Hello everyone, Wacker Process. Myself, Dr. Digna Varghese. Wacker process or oxidation of alkanes. It is the catalytic addition of molecular oxygen to an alkene. Here you can see ethene. The molecular oxygen is added to ethene in the presence of a catalyst, that is tetrachloride of palladium 2, and in water it, the alkene is converted into aldehyde. There are three important sources of molecular oxygen in the reaction. They are carbon monoxide, water, and molecular oxygen. The catalyst used in this process is palladium 2 chloride, that is PdCl4 2 minus. Its IPC name is tetrachloride of palladium 2. Copper 2 chloride is used as the co-catalyst in the presence of dilute HCl in this reaction. So Wacker process or oxidation of alkane is the process. It is the catalytic addition of molecular oxygen to an alkene and it is converted into aldehyde. Wacker process or Hoechst-Wacker process. This process developed in Germany. 4 million pounds of aldehyde synthesized by this method. The Wacker reaction was first reported by Smith et al. Wacker process began in 1956 at Wacker Chemie, the chemical company. At the time, many industrial compounds were produced from acetylene, derived from calcium carbide, which is an expensive and environmentally unfriendly technology. Wacker to investigate a cheaper raw material, a reaction of ethylene and oxygen over palladium on carbon in a quest for ethylene oxide, unexpectedly gave evidence for the formation of acetaldehyde, simply based on its smell. More research into this ethylene to acetaldehyde conversion resulted in a 1957 patent describing a gas phase reaction using a heterogeneous catalyst. In the meanwhile, Hoechst AG joined the race. Heterogeneous process ultimately failed due to the catalyst inactivation and was replaced by the water-based homogeneous system for which a pilot plant was operational in 1958. Mechanism of Wacker process. In first step, the addition of an alkene into the complex and forms a metal olefin pi complex. Here you can see the complex is the catalyst here and the addition of an alkene to this complex and forming a pi complex by the removal of a chloride ion from the catalyst. Therefore, two negative charges reduced to one negative charge. In second step, the hydration of the alkene palladium 2 complex occurs by the attack of water molecule from the solution on the coordinated ethane rather than the insertion of a coordinated OH. It is indicated by the stereochemical studies. Here you can see the OH from the attached to the coordinated ethane rather than the insertion of coordinated OH. So here forms a complex. The hydration of the alkene palladium 2 complex occurs by the attack of water molecules from the solution on the coordinated ethene. In third step, here you can see the compound, the coordinated hydroxyl group complex isomerizes the coordinated alcohol first, and there is a beta elimination occurs with the formation of a pi-vinyl complex. What is beta elimination? It's a chemical reaction in which atoms or groups are lost from the adjacent atoms, resulting in a new pi bond. Here you can see the one of the chloride ion is removed and forms. There is in the pi vinyl complex there is two chloride ions, and one of the hydrogen is eliminated to this, and here forms a new pi bond and forming a pi vinyl complex here. Fourth step. In fourth step, you can see the pi vinyl complex undergo migratory insertion reaction. Here you can see the pi vinyl complex. By the addition of a chloride ion, this part is converted into PdCl3, and in this the coordinated pi vinyl part, this there is undergo a migratory insertion reaction. Here you can see CHOH. In this part, a hydrogen is migratory inserted and forming a Cl3PdCHOH CH3 2 minus complex. The elimination of acetaldehyde and hydrogen ion then leaves palladium 0. Here you can see this complex in which the acetaldehyde part is eliminated, that is CH3CHO from this molecule, that is the product, and 2Cl minus 1HCl and palladium 0 metal form. The palladium 0 is converted into palladium 2 by the co-catalyst, that is copper 2 catalyzed air oxidation cycle, and the cycle can be broken down into three reactions. Here you can see the catalyst reacts with alkene in the presence of water, forming acetaldehyde. That is, Wacker process is the process in which the molecular oxygen addition to alkene in the presence of a catalyst, there is an oxidation reaction occurs and alkene is converted into aldehyde, and leaving behind the palladium metal here. This palladium, after Wacker process, the palladium 2 chloride catalyst is converted into palladium 0 metal. So the palladium 0 is converted back to palladium 2 by the copper 2 catalyzed air oxidation cycle. Here you can see the palladium 0 reacts with copper chloride. In the presence of HCl, it is converted back to palladium 2 chloride, and the cupric chloride converted into cuprous chloride. The cuprous chloride again converted into cupric chloride by the molecular oxygen in the presence of HCl. So these three steps involved in Wacker process, and by the Wacker process the alkene is converted into aldehyde. So Wacker process in general, it is the molecular oxygen addition to an alkene in the presence of a palladium 2 chloride catalyst, and the alkene is converted into aldehyde. Wacker process. This is the representation of a catalytic loop. Here you can see the catalyst to which the alkane is added. By the elimination of a chloride ion, it forms a pi complex. By the addition of water molecules, the pi complex converted into a coordinated alcohol compound. It will undergo beta elimination reaction and forming a pi vinyl complex. Pi vinyl complex undergo migratory insertion reaction. Here you can see the Cl3PdCHOH CH3. This compound undergo reductive elimination reaction. By this process, we will get the product, that is alkene is converted into aldehyde and leaves the palladium 0 metal. So its catalytic efficiency is needed further. So this palladium 0 is again oxidized to palladium 2 by the copper chloride co-catalyst cycle. Here the cupric ion reduced to cuprous by the presence of molecular oxygen and HCl. So palladium 0 is converted into palladium 2 metal catalyst. So the cycle is repeated several times. By this copper cuprous cupric conversion, the alkene is converted into aldehyde by this process. Role of palladium. Palladium coordinates alkene, thereby weakening the carbon-carbon double bond. Palladium coordinates hydroxyl ion, thereby ensuring the close proximity of hydroxyl and alkene. The coordination of alkene to palladium removes more electron density from the pi bonding molecule of alkene, thereby rendering the alkane more susceptible to nucleophilic attack. Importance of co-catalyst. Without cupric chloride as an oxidizing agent, palladium 0 metal would precipitate, stopping the reaction after one cycle. Industrial process. There are two types of Wacker process. Here we are discussing the one-stage Wacker process. Here you can see the industrial reactor system, and here in one-stage process, ethylene and oxygen are passed concurrently in a reaction tower at about 130 degrees Celsius and 400 kilopascal. Okay, the catalyst is an aqueous solution of palladium chloride and copper chloride. Here, ethylene and oxygen, which is passed through the catalyst in a reactor, there is a separation occurs. The ethylene is converted into acetaldehyde and some ethylene gas is unconverted and the catalyst is separated here. On cooling and washing, we will get unconverted gas here. This is again passed into the reactor tower and by the catalyst it is converted into acetaldehyde. Okay, after cooling and washing, we will get a crude acetaldehyde here that will undergo purification by extractive distillation. Here, the lower boiling point compounds impurities separated and we will get somewhat pure acetaldehyde than crude acetaldehyde, but here is also some impurities with this compound. It will again purified by fractional distillation and we will get pure acetaldehyde here, and the impurities, that is higher boiling point impurities or byproducts, are separated here. Due to the corrosive nature of the catalyst, the reactor is lined with acid ceramic material and the tubing is made of titanium. Here you can see oxygen and ethanol is passed to the reactor preheater system into the reactor. Here the reactor, the conversion occurs. After this conversion, it is undergo distillation, extractive distillation and also fractional distillation, and we will get 99% acetaldehyde, that is the oxidation product. In the case of Wacker process, alkene is converted into acetaldehyde. Here we are discussing two-stage Wacker process. In two-stage Wacker process, the reaction and oxidation are carried out separately in tubular reactions. Here you can see ethylene is taken, catalyst is taken in another tube which is in contact. Here catalyst is coming in this way and ethylene is coming in this way. So it is a two-stage process. In the case of one stage, both ethylene and catalyst is mixed together. But here it is separated and coming into contact here and forming acetaldehyde with water vapor. Used catalyst is converted, separated here, which is here the used catalyst is as separated as palladium 0, which is undergo oxidation, and the catalyst is regenerated here. It is again passed into the catalyst tube. Okay, here we are getting the acetaldehyde which undergo separation, and we will get the crude acetaldehyde which will undergo distillation process for further purification. Here lower boiling point impurities are separated here and acetaldehyde with some impurities is again separated by fractional distillation and we will get the pure acetaldehyde here. So this is a two-stage Wacker process. So in industry there are two types of Wacker process. In both the case the alkane is converted into aldehyde, but in one stage process both the catalyst and the alkane is mixed together, but in two-stage Wacker process both the catalyst and ethylene is separately entered into the reactor, and in reactor there is mixing occurs and acetaldehyde is formed. Thank you for your attention. Bye for now.